Moi, hello. My name is Konsta Hölttä. Some of you might know me by my nickname Sooda, which originates from the Finnish word koodata, coding. I'm a system software engineer at Nvidia, and I'm here to tell you about graphics processing units. But first, let's get the businessy part, the mandatory one, over quickly. So here's something about Nvidia. It says that we invented the GPU, which is marketing term for the version of the GPU that has the transform stuff in hardware that's effective for transforming vertices to the screen and doing all the rasterization and stuff like that. There have been several graphics processing things in the past. For example, the Amiga had its own GPU, but not a desktop GPU as is. And Nvidia Helsinki is located in Ruoholahti, and it's a daughter company, tytäryhtiö of the big Nvidia. And most of you perhaps know Nvidia by just the graphics chips, but we do a lot of more things also. Nvidia is today called the visual computing company or something like that. And in the picture you see the Aalto part is, I think that's from the Tesla Model S, which contains a Tegra system on a chip that part of the Helsinki team is developing. And Enterprise is just the Quadro cards for big CAD softwares and stuff like that. And HPC, high performance computing, is for, just the supercomputers and small stuff like that. And well, what does Nvidia Helsinki do? Here, that's the Pixel C, the Google tablet that's actually running the open source Nouveau kernel GPU driver. And on the right, you see the best Android TV, the Nvidia Shield console. That's like something like 200 euros. And on the bottom, there is this Tegra X1, the Jetson X1 that contains the X1 chip. That's for embedded programming. That chip is like, the board itself is a bit bigger than a credit card. And the last one is a tablet that's slightly older than the Google Pixel C. But it's the second most powerful tablet that there is. What's coming up? That's the Drive CX and Drive PX, the automotive boards. And I have the other one on my desk. I'm developing the GPU drivers for it. CX is the cockpit computer designed to make your cockpit more cool and to drive several displays in a car. PX is the pilot computer that's supposed to drive your car autonomously. We're striving to make that happen soon. And the headcount is nice power of 2 plus some summer interns. And our office is in Ruoholahti, right at the end of the Länsiväylä in the blue old Lepakko building. And we do mostly just Tegra system on a chip development. And the Tegra chip is a GPU and then all the rest of the computer on one chip. We also do deep learning and stuff like that. We have the 3D team that designs the future of our GL drivers, and a display team that makes the display work when you have the graphics on the computer. It drives the output to the HDMI and stuff like that. And we also try to make WebGL work smoothly. Then kernel team is where I kind of live in. I'm working on the low-level graphics and the host interface that drives command buffers to the GPU hardware. We also do power management and stuff like that so the chip doesn't overheat when you're using it. And the build team tries to maintain our continuous integration where each patch that we submit in the Git repositories goes through dozens of tests. And everything would break if we weren't fixing it all the time. We also are very good at detecting cars in pictures. We're like the top one in the Kitty benchmark. We're even better than our headquarters team in this benchmark. We also do cameras because the future autonomous car will have like dozens of cameras. We can only use 12 at the moment. And every camera needs a different lens correction and stuff like that in the hardware to be able to process all the frames, 60 frames per second. The research team looks into the future and tries to shape our next GPU architecture so that it would work well with some algorithms that the guys see will be useful in the next few years. And the content tech guys work with game companies to optimize their code so it works better on GPUs. Yeah, and the mandatory slide. I copy-pasted these from our previous slides, so mostly. And if you're good at low-level graphics programming and know how a computer works, then come talk to me afterwards. That's that. Any questions about the company? Nope. Let's move to the actual presentation now that the mandatory part is over. So I'm still Konsta, and the point of this presentation will be the modern GPU architecture and how it works, why it's so fast, why it's not so fast when you're trying to use it and you have got some bugs or design bugs so that it works slower than your CPU even though it has a couple of thousand cores. Yeah, I said that, but I'm only talking about the Nvidia approach to this. I don't know how the details of AMD or Intel or things work, but the basic principles are the same, and I'm trying to keep this on a high level, but also include some details for the more knowledgeable people in the audience so that you wouldn't be bored. And obviously I'm working there, but I'm working in the interface between user space and kernel. I'm not seeing triangles every day. I just see some numbers going through and passing buffers in there and trying to synchronize the hardware to work with all the user space applications. This presentation will be roughly following the link in there, the life of a triangle. That's a very good article about GPUs in general. So how does GPU actually work? What do you do with it? Or what do most games and demos, how do you use it? Well, they render zillions of triangles, and the triangles are just numbers. The GPU uses lots of numbers in a buffer, reads them, and then outputs them rendered, like projected on a 2D plane on the computer display. So on the screen now you have two different triangles presented as the GPU system. And that's in OpenGL, that's for example the GL draw arrays or draw elements or whatever it's going to be called. And that maps pretty close to some GPU method on an object in the hardware itself. The hardware is quite intelligent, so there's a lot of details that the driver itself does to validate all the state and stuff like that, but the hardware has lots of triangle-specific stuff, even though it's also useful for general purpose computing. That's what you would see, and that's what the vertex shader does when it gets the input. Vertex shader is the small piece of code that's run for each vertex, and if you have vertex location that's, for example, in the origin, how does that map to the display? Where is it? So you have a matrix that specifies the camera that is just a matrix transformation that moves the pixels to some location, and that also projects the 3D to 2D. And it doesn't see field triangles yet, that's just the vertices. And now if you move to pixels, those are quite small triangles because they cover now just a few pixels. The fragment shader takes the corner locations, that is the vertices, and fills or rasterizes the pixels that fall between the triangles and produces color for them. And that's the fragment shader because it has more information about the pixel than just the pixel color. It's got the Z value, that is the depth, and all sorts of more input, and the output is also maybe more complicated than just pixel, and it may be a texel, that's the texture coordinate in the picture if you're not drawing to your usual screen, but some sort of intermediate picture. So we had the shader presentation yesterday, and I'm going to tell a little bit about the two major cases where you're using the shaders. That's just for the fragment shaders. The picture on the left is from the Nvidia IRA demo that's rendering a pretty realistic human face. And that's got something like 4 different shaders in it. One is for the skin, and you can see that there is some sort of directional light coming from approximately where the camera is, and then somewhat up from that, because you see the white stuff on the skin. And then the other part second shader would be for the eyes, because they are so different from the skin, so it makes sense to write a different program to shade those. And then there's also, I think there's one shader for the teeth, because they are different and they are not part of the skin itself. The skin is different mesh. And there's a fourth shader in the background that just generates this white background. And the one on the right is just, I think it's one full screen quad, that's 2 triangles. And then there, the approach is completely different. You don't have lots of triangles that are submitted to the GPU for rendering. In the face, you have very small triangles like that fit just a few pixels, and then you shade the pixels that fall in between those. And on the right, you just loop through every pixel, and then for every pixel you have this arithmetic computation that determines some approximation for, in this case, like a point, some sort of simple camera model that shoots rays from one point through this picture plane that your picture comes in, and then it projects the 3D on that, and does that all with just math without any triangles, and doesn't rasterize the triangles, but the color that you find out in the shader. So what sort of GPUs have there been? Well, the first real big GPU came in August 1999, and today we are in 2016, and there have been a couple of different DirectX and OpenGL versions in between, and the Tesla was perhaps the first architecture that had this unified shader language or architecture. That means that for every vertex and pixel shader, you run the same, the shader runs on the same hardware. There are no specific parts of the hardware that would run just something specific to vertices or pixels, and that's also where CUDA came in, so that we could use GPUs for arbitrary processing of huge amounts of data. And what's the GPU today? It's got these big numbers, but what do they mean? If you compare that to pretty much the latest Intel CPU, the 9 teraflops means that you can run 9 gazillion of floating point operations per second, and that's like 10 times as large a number as the Intel CPU, or I mean not even 10, it's more like nearly 100, depends on the case. And the power it uses is just about twice as much, 180 watts per one GPU. And what does this 2,560 CUDA cores mean? Well, it doesn't mean that you can run an operating system or just arbitrary program on each one of those. You just run the shaders that are very specific to the GPU hardware. GPU is a super parallel work distributor that has just these very simple dump cores that are not much more than just ALUs, arithmetic logic units that sums numbers and fetches some data from the RAM and does things like that. It doesn't have anything complex as today's CPUs do have. CPUs are very good at doing this thing on this number right now, but GPUs are very good at taking lots of data as input and then producing pixels as output, and you don't really care when does this exact pixel get rendered. And the point is just that you have these pixels, but you don't care when each pixel gets rendered, you just want the whole thing. And that's where the latency hiding comes in. You literally have to run like over 9,000 threads on it. Thread is like a process. It's a separate thing from all the other threads, just computes something and then has some output. In Nvidia hardware, you have these warps that consist of 32 threads. And the single instruction multiple threads is like single instruction multiple data simmed that CPUs can also do, but CPUs don't have that much cores. The latest ones have like 4 and 6 plus hyperthreading. And all the 32 threads run in lockstep. That means that for every line of code in assembly, it's not like you have got the shader language and then for each of those lines, but each instruction at the machine level runs at the same time on every one of those. So it makes the hardware much more simple because you can just have one version of the program counter that specifies which instruction is running right now. And then if, for example, all the 32 threads are waiting for RAM access, then the fast scheduler can swap those out and then take some other threads in a very short amount of time, just a few clock cycles. And because they are running lockstep, if you have any ifs or elses, that means the branches, you run actually both of them because they all have the same program counter, so it has some special hardware to mask out the outputs of some of the computation so that you just run both branches and it's slower, but it just goes like that. Here's a picture of a GPU, render on the GPU, and that has just the colors that are the usual outputs. Here we have every vertex colored by the streaming processor ID. The GPU has a number of streaming processors, and each of those has a number of warps. So you see that pretty much every vertex goes to some SM, and then there are no particular ordering with the brightness or the yellowness of the pixel in here, but it just means that different pixels go to different CPUs. I mean threads in the GPU. Here these tiles are, I think they're 32 by 32 pixels, which is how the Nvidia hardware divides the processing when you get some input. And the fragment ID is so that for every constant color in there, you have the same streaming multiprocessor running, and then you see how it parallelizes for everything. And then inside every of these tiles, you have, for each pixel in there, you have a different color, or not exactly. If you go one step further from here, you get the thread ID, but here warp ID is inside this streaming multiprocessor, and it means that you just see how the GPU loads schedules the work for different of those warps in here. I've got a practical example of what's a bad fragment shader and how you could optimize it. It's not very relevant to this particular event because usually when you're writing demo code, you just want some artistic stuff, but not very, very performing stuff, because you can have simple geometry that even looks cool. But let's anyway look at this. You have this checkerboard pattern that comes when you sum the x and y coordinates and then take the modulus with 2. That's jakojäännös. It produces checkerboard pattern. There are 1010, 1010, and 010101. And then I have this bad example of choosing this big heavy function for either the red color or the green color. And then for the checkerboard pattern, it means that within each warp, every thread runs the same code. But what happens when you have 2 of these branches, each one of them computes both of those, and then half of them discards one of the color, and the other half discards the other one. So you run twice as slow as you could. And then maybe it was a bad example because I would expect a clever compiler to modify the code to this so that you just run the expensive function once and then determine if you run the assignment that is fast on either one of those. But we can go even better. You usually should not use any if statements in the shaders, because that's how you avoid the branching. You should use arithmetic. For example, in here you have this flag and one minus flag, and that works for the checkerboard pattern. It selects if the red or green pixel is colorful or not. And then you should also use these vectors instead of plain floats, because that's how the compiler usually can fix your program to know that these two values are independent, and it can schedule the computation to be parallel. And constant global branches are, by the way, just okay if you have these long lists of ifs, that if time is less than this or less than this, then choose this particular object to be rendered, because that's the same for every pixel. So then you don't have the two different branches executed, so it's just fine then. And then I have the more practical example further, that's how you can parallelize stuff. On a CPU, the red code would be particularly good, or just fine, because the CPU doesn't do anything parallel. It just sequentially updates the sum to be the sum of every array element. But on the GPU, you have these different cores that run completely different code, and they should have completely different input. And if you would sum something, that just wouldn't work. And then I have this green colored example that the first loop would be parallel, so that the contents of that loop, the second smaller loop, would run on different threads, and you would have like 1,000 of those. And then just at the end, you've run this last for loop just 1,000 times instead of 1,000 times 1,000 times to sum over the elements. And then the different threads would run fast, and then the last computation would be also fast. And then, yeah, I just talked about how the cores work, but there's also lots of graphics-related stuff on the hardware. And the cores work for every sort of shader, which is about the unified shader architecture. And for the guys that know what a CPU register means, on a GPU you don't even have those, but you have just local memory close to the warps and the stream processors that select the registers in the memory. And then you have this vertex/fragment scheduling thing that takes the vertices input and processes those, that is just 3D specific instead of like just summing over an array. So there are several things in the chip dedicated just for that. And the last thing is pretty important for general graphics in games and demos, that if you, for example, sample some texture in the pixel shader, you should compute the texture UV coordinates in the vertex shader, so the hardware can kind of preload the value from RAM before even running the fragment shader. Things like that can help in hiding the latencies. And even though the GPU can run like hundreds of gigabytes per second, even when you're rendering a full HD image at 60 frames per second, just writing the pixel values out is 500 megabytes per second, nearly. And usually you have several passes, for example, like doing motion blur or something like that, and then reading all the vertices and the textures that are used for coloring the vertices. So you quickly have a lot of data. And then that's not really a problem if these fit in the bandwidth, but the problem is that you have to wait for each memory fetch. So if you load something from memory to a variable, that actually takes time. And if they are scattered around memory randomly, then that doesn't really work, because each memory access is slow, and you should kind of coalesce the accesses so that memory access would be sequential, so that, for example, when you have these different threads running on same warp, it's very good if all of those could fetch from some array the values that are close to each other, so that you would access the memory so that the place where you load values would be close to each other. So the memory units can actually, because they usually do fetch memory in like 64 bytes per one fetch. If you just read one of those and discard the others, then you waste all the bandwidth. And the AOS versus SOA means arrays of structures and structures of arrays. So usually if you read something in a big computation, you should have those values close to each other. And for example, if you have some objects that have different properties like color and some other color, so you can either make structures of those different colors and then do an array of those, or then just have plain arrays of all the colors of this one thing and then another array for the colors of the other things. And just separating the data this way can yield you significant perf benefits. And a draw call is something that is visible in the code as draw elements or draw arrays. And that also maps quite close to the hardware, but then it involves lots of expensive state changes and especially state validation in the driver. And that's more advanced stuff. You can ask me later if you want, but that's something that this Vulkan API tries to fix. And when we are going from the OpenGL or DirectX API back to, all the way to the hardware, first the API goes to the driver that validates stuff and then formulates push buffer that's full of commands for this particular hardware that specifies what kind of state you have to set up to make the rendering work. And then that goes to this host interface. That's the piece I'm working at. That's in the kernel that writes to the host hardware registers directly. And then that goes to this front end piece that does context switches. That's kind of like the CPU does context switches, that when you're running different programs, you can actually run those at the same time instead of like starting one and then closing that and starting another one. And that's why the shader toy front page is so heavy that I think that every GL context is a different process in the GPU, and the GPU switches between them. It runs one context for a while and then switches to another one, and there is some overhead in switching between these. And then if you have dozens of those visible at the same time, it kind of gets laggy in addition to having lots of work for the GPU actually. So that's my last slide. The point is just that when you're writing some algorithm for the CPU and then have that perfected and runs very fast for that particular CPU, you can't just write that in the shader code and expect it to run fast. You have to think completely differently, just like, for example, in summing over the arrays. You have to split the problem in smaller parts and then combine those afterwards. And then also there's more than this presentation, like how the displays work and how color spaces work and how the displays talk to the GPU and how power measurements work and everything. That's kind of complicated also, but that's not relevant in demo coding. And demo coding is anyway more art and science, that you can just play with things and have colorful things on the screen instead of just having some game engine that actually is a result of tens of many years of work. And then even in game companies, when people are optimizing these shaders, the optimization methods are like trial and error instead of just knowing what to do exactly, because the compiler that compiles the shaders on the particular hardware is complex, and then you can just shuffle some code around and the result is the same, but the code runs still much faster and you don't know why, but it just occurs that, and then you can be happy with that. That's about it. Thank you. Any questions?
Just a quick general question. So, the CUDA codes, right? At the hardware level, are they treated any differently from when you're processing a graphics workload?
Are they what different?
Are there any hardware? Are they different in terms of the hardware? like multiprocessing goes?
No, the question was, are the CUDA cores somewhat different when you're doing different computations? No, you have inside these streaming multiprocessors, you have these warps that run the threads, and then the streaming multiprocessors are inside GPCs. That's a graphics processing cluster, and then a GPU has multiple graphics processing clusters, and each of those have some specific things on that piece that is multiplied for, like a GPU. Big GPU has 4 graphics processing clusters, but each thing inside those is completely identical to the other ones. So if you have like 2,500 of the CUDA cores, all of those are identical.
So in some sense, are the SMs and the CUDA cores the same?
No, the CUDA cores are inside an SM, and SM contains the scheduling stuff for those. So a streaming processor contains like about 100 of those cores. And then the problems work when you just parallelize the thing so that you have the set of inputs and then some set of outputs, and then the different threads don't exactly need the input of any other threads. Did you have something? Yeah?
What causes the stuttering in multi-GPU setup?
What stuttering are you exactly referring to? The question was what causes stuttering in
Monitor, like when you use it.
human tearing?
No, I mean, why it's preferable to have one GPU over two GPUs?
Sorry,
GPUs
I'm not hearing you.
Stuttering.
Say it again.
What?
You're too far away, I can't hear you.
What's sounds voimat?
Yeah. You can ask in Finnish also.
Miksi multiplayer, siis enemmän näytöohjelmia on huonompi vaihtoehto kuin yksi näytöohjelma?
Onko?
Joo.
Miksi?
Koska se on todettu, että niinku, ne siis vie enemmän virtaa, ne näytöllisesti tapahtuu semmosia virheitä, että ne ei synkronoi oikein.
Yeah, the question was about having multiple GPUs driving just one display, and usually it's good to have multiple GPUs so that you can divide the work for all of those, and each of them computes just one part of the problem. But it's usually first it's hard to formulate the problem so that it divides well, and usually if the driver can just try to do that, it's one of the most complex things in the GPU driver. That's with the SLI setup that you have these different GPUs. And for example, if you are just rendering one scene with multiple GPUs, usually all the GPUs have to have the same memory. So if you have 2 different GPUs and each of those has n gigabytes of memory, you cannot just sum them up and upload that amount of memory in there, because one of them is running, for example, the upper half of the frame, and the other one is running the bottom half. So you need the same geometry in both GPUs and stuff like that. So it gets pretty complicated, and it's easy to make errors in those there. I don't know what exactly would cause stuttering or anything, but it's hard.
I guess it's just that it's also easy to predict how much workload you will get from. Even if you play like top or bottom, how do you know how much workload you will get from the top layer? So probably because it's very difficult to know what. There's no way to predict optimally what should be unless
Yeah.
it's a very predictable scene.
Yeah.
Something similar rather than trying to run a military program. How do you divide your work between 2 CPUs?
Peter noted that
Very easy
it's hard to predict if, for example, you're splitting the scene in between the display to be rendered partially in one GPU and partially in another one. It's hard to predict if you just split it in the middle, the other part might contain a lot of more geometry than the other one, and then one of them finishes execution before the other one, and it's hard to predict how you should optimally divide workload. That's an important thing.
Yeah, I think that's a big problem. Especially if you're in a driver level, it's probably even more complicated because then you're already lacking some of the information in the application.
Yeah, for the driver it's hard because it doesn't have the detailed information about your game. Anything else?
They changed the idea that the application should be responsible for its scheduling.
Anything else? Okay, thanks.